Okay, hi all, and welcome to Advanced Security Exploitation, or ASE. I'm Tom, and I'm going to be a tutor on this module alongside Cliff. So the first topic that we're going to be looking at is it's a bit of a recap of some of the topics that we've covered in the undergraduate modules. So we're going to be going over familiar concepts like software vulnerabilities and exploits, but hopefully we're going to introduce a new way for you to think about software vulnerability and exploits that will be useful throughout the module, particularly later in the module when we start looking at exploit development. So before we get into the detail of how exploiting vulnerable software, how we are actually going to be exploiting vulnerable software, it's worth taking a step back and looking at the high level concepts involved. So first we're going to look again, we're going to try and define what we mean by secure, what we mean by software, what we mean by vulnerabilities. We're going to look at one of the ways we can categorize software vulnerabilities. We're going to look at the different sources they come from. This is going to be a bit of a foreshadowing of a future video which I'm going to put together and release that goes over an overview of different categories in more detail, different ways that people have categorized software vulnerabilities. Following that, I'm going to introduce introduce the conceptual framework of the weird machine. So weird machines is a way that it's commonly used to describe the functionality that a program has, or a machine in the abstract has, that the designer did not intend. And exploitation is the final slide is going to be on exploitations. We can think about exploit development as programming this weird machine. It'll become more clear what I mean by this later in the lecture. Okay, so what do we mean by secure? So one way of thinking about security can be in terms of security objectives. So objectives for either an organization or the objectives of a system, or the ways that a system can be used. Okay, so the most common way we present this in the security field that you've probably seen before is a CIA triad or CIA triangle. That's on screen now. So security can be described in terms of the following three objectives or goals. Confidentiality, so keeping information or data private. Integrity, so keeping data or information accurate, complete and consistent, particularly when we're passing data between internal components of the same system. That can be a big cause of security problems if we're not consistent. And availability. So availability is keeping data accessible by people that need it when they need it. So security objectives, these three objectives are often, for a start, it's actually hard to categorize all security objectives. They don't all neatly fit into one box, so it's more of like a spectrum. Some of the goals or objectives that you have might fit into multiple categories. So these objectives are often at odds with organizational goals. So the number one organizational goal of a business is to maximize profits. Historically, it's been it's common. It was common for businesses to just completely forego investing in security because they saw it as an unimportant expense. Thankfully, legislation like GDPR's come along, which gives the government powers via the ICO to impose massive fines on companies that aren't treating data security seriously anymore. So now it's thankfully that's managed to push the balance a bit more in favour of companies opting to secure their data and treat the data security seriously, rather than just shrugging it off and thinking, oh well, so what if we get a breach? I mean, and just taking like the reputational hit, chalking it up as a business expense, basically. They can also be at odds with each other, so confidentiality and integrity can be at odds with availability. An example of this can be found when we think about how we handle a potentially risky state of memory, so or a particularly risky state of the program that's running. So good example, we can find concrete examples of this. So one of the benefits of the of open source software and processes, like with the Linux kernel, which is the example I'm going to use, is that we get to see some of the discussions of these issues taking place in a real world setting. So we can look at the Linux kernel mailing list for there have been like a bunch of threads and discussions between different maintainers and engineers talking about exactly these problems. So in the description and in the references slide at the back, there's a link to a particular article that's quite funny, that also gives insight into this back and forth tug of war between the different security goals. So there's a discussion between Linus Torvalds, the creator and maintainer, benevolent dictator for life of the Linux kernel, and he's arguing with a security engineer called Keys Cook, that who works for Google. Cook has put together a patch for that introduces some hardening features for user copy, which essentially the gist of the patch is they introduced some whitelisting, so that if some particular security conditions were not met, the kernel would just crash and panic. The kernel will panic. So think like Windows blue screen of death, just like shut everything off, kill the machine. If we entered this risky, this potentially risky memory state, which may or may not have been actually a result of an actual exploit. It could just be the case that the programmer there's been a programming mistake that could potentially lead to an exploit. So this is an example in the real world of a conflict between availability and integrity, and availability and integrity and confidentiality combined, I suppose. So Cook being on the side of keeping confidentiality of prioritizing confidentiality and integrity, and Torvalds being on the side of prioritizing availability. So it's an interesting read anyway. I recommend having a look. There's an article, I've linked both the article and the original mail thread in the description. Okay, so what do we mean by software? So at a nuts and bolts, what's actually happening, level, software is just collections of instructions and data that are running on a CPU. So it'll become obvious later in the module that the distinction between instructions and data is not super clear, particularly when we can get down to a really low level and look at how the CPU handles data and instructions with its internal registers and internal state. So software is typically code that's written by a programmer that's typically not in a in assembly language, that gets compiled down into machine instructions, and it's usually an attempt to implement some abstract design specification that may or may not have actually been defined or written down. So like I might have an idea of some ideal system that I want. By definition, an ideal system would have no bugs or security problems, obviously. So what are some of the ways we can think about systems in the abstract? So a good way of thinking about it that's pretty useful is a finite state machine. So this is used in computer science a lot, in theoretical computer science. It's a computational model for representing an abstract machine. So an abstract machine is something such as a computer program, and it represents it in terms of the states that the machine can be in, and the transitions between these states. So the picture on the screen, the states are represented by the circle, and the transitions are represented by arrows, with the source of the transition annotating each arrow. So the picture example that we've got is a finite state machine of a turnstile locking gate. So think about like the toilets in the train station, like with the kind of turnstiles which require a coin. So there's two states it can be in. It can be either locked or unlocked. If it's locked and you push it, nothing happens. If it's locked and you put a coin in, it becomes unlocked. If it's unlocked and you put a coin in, nothing happens. It doesn't become locked magically. They might get stuck if there's some kind of mechanism. But this is a very simple, representation of what the system actually is. We could add other states, conceivably. And the final transition is if it's unlocked and you push it, it'll become locked. So for more complex diagrams, we can imagine how any system could be modelled in this way. We could write about the potential of good states that a system can be in, and the bad states that, and the transition between the good states. And if we had an ideal system with perfect design, with the as designed as well as we possibly could, we could imagine that there would be no security problems in that, by definition. So other ways that we can represent abstract design specifications of a system that we're wanting to build is that you might be familiar with UML. So UML is a diagramming language, unified markup language it stands for, and it was used more in the past than it is now, but it's still used in business to design and describe software systems, and not just software systems, but just systems in general, in terms of components and the relationships between components. And if you want to go really specific with your specification and you want to be as precise as possible, you can formally specify what your system does in a language like Z notation, where you're using mathematical symbols and characters and set theory in order to define exactly what the system should be allowed to do and what it shouldn't be allowed to do. So, vulnerabilities. What are vulnerabilities? So vulnerabilities are weaknesses in security. So properties of a system that can be leveraged to negatively impact our security objectives. So anything that, so when we're thinking about vulnerabilities, it's useful to consider what the designer actually wants the software to do. So the security problems, by definition, aren't in the ideal finite state machine. So think about this. There's a picture of a developer who's thinking about a perfect system, or the system, how he intends it to be. Now the actual interesting stuff happens in the gap between the ideal program and what the, so i.e. what the developer wants the system to do, and only those things, and what it can actually do in reality. So in reality there's often additional things, or you can often use the system in strange ways. So I've got an example of this now that we can watch. This has been a video that's been going around. I thought it was quite funny. It's actually talking about QA testers, developers watching QA testers test a product, rather than security testers. But we can see how we could. We'll watch it.
Can you guess which spot that goes in?
The square.
That's right. It goes in the square hole.
Yes. Okay.
And how about this rectangle? That one
Also the square.
goes in there too.
Yeah.
Up next, we've got this thin rectangle.
The thin rectangle.
Can you guess where that goes?
The thin rectangle.
That's right. It goes in the square hole. And up next, a cylinder.
The circle.
I think that goes in
The circle.
the square hole. Now, we've also got this semicircle right here.
She looks
Do you see a
progressively
spot
more
that would fit
The semicircle.
distressed
The
as the video
semicircle.
goes
That's
on.
right, it's the square hole. Okay. Up next, the triangle. We know what hole that goes
The
into,
triangle.
right?
Triangle.
That's right. The square
So
hole.
we could imagine.
And up next, we have the arch.
The arch. The
And
arch.
you guessed it.
The arch.
It goes in the square hole.
So she looks a bit unhappy about the way that people are using using a system. So we can imagine that with a better design, this wouldn't be a problem. So we could imagine potentially having like tags on the side of the square so that only the square fits through the square hole, nothing else. Like that's probably the intent of the designer. They'd probably like you could imagine an alternative system where, or we can also imagine how this could potentially map onto security testing. So there might be like ways into a system that you only want certain shaped holes to go through, or user accounts or whatever, you know. So we are going to be doing a lot of putting things through square holes and seeing what happens during the course of this module. So what we want to, we want to see how the system can actually be used rather than just the way the designer wants it to be used, despite whether it ends up upsetting the developer or not. Okay, so sources of software vulnerabilities. So this is just a brief slide. They often come from 3 different sources. Design problems, so things like the thing we just looked at was a design problem, and we can think of in terms of security. There's a good example, which is not exactly software of vulnerability, although the fixes have been implemented on the software side. You can think of things like Spectre and Meltdown, which did predictive branch calculation in the CPU, which ended up, it was a massive design problem. It ended up the discovery of these vulnerabilities essentially meant that you could sometimes read data that was pre-calculated and stored in the cache in cache memory. Essentially, the design of the system was vulnerable inherently, because you could read data that you shouldn't have been able to read. So you could read down branch paths of an executing program that would never actually be reached. So if I'll leave a link to a write-up in the description if you're interested about that one. So misconfiguration problems, things like sharing a drive over the network, or maybe you might have misconfigured a FTP server and left it open to anonymous users. You might have default. You might be using a system without actually understanding exactly what the configuration that you're using, what the implications of that are. So implementation problems, aka bugs, software bugs. These are the ones that we're going to be looking at primarily throughout the course of the module. So things like poor input validation, memory mismanagement, and programmer mistakes leading to these things, or race conditions are implementation problems that we'll be looking at later as well. Alright, so at the start I mentioned that I'm going to introduce a new framework for helping think about exploitation. So this concept of weird machines was introduced by Sergey Bratis, a professor at Dartmouth who works at DARPA, and he's one of the people, and it was later built on and formalised by Thomas Dulian, who's Halvar Flake on Twitter, who works at Google Project Zero. So I've included in the references two papers, one by Bratis, which I would recommend reading, and the other by Dulian. So Bratis introduced the idea, and then Dulian worked on it and formally defines it later in his paper, which is interesting. But and you can read it if you're interested. I'll leave it at the end, but I would definitely recommend reading the Bratis paper because it gives you an overview of the history of exploitation, and it's really interesting. A lot of the things that we're talking about through this module are explained briefly in there in a historical context. So the weird machine. The weird machine is the bit that sits. The reason I was first introducing the idea of this ideal program that has no problems, what the programmer intends on being able to do, the machine that the programmer intended to create, you could think of it like the actual program has lots of extra functionality, and generally, and you can do things that, if the programmer hasn't been very strict with defining the specification, which it's very hard to do, there are probably gaps between the ideal program and what's actually running. So the weird machine exists in those gaps. So there are odd things you can do that. Okay, I could think of a good example of a weird state. So a state that your system can get put in would be one that isn't included. This is how Julian defines it, and I think he's right with his description. It's one which fits within the it's not found within the ideal finite state machine that the programmer has come up with. So the programmer has an idea in mind, and the program can do other things. So an example, I don't actually have a picture ready for it, but an example which you may or may not be familiar with from when I was younger. There was probably the most widely, I don't know, it was a very visible bug. In Pokemon Blue and Pokemon Red, the Game Boy games, there was a bug a memory corruption bug, which allowed you to you could corrupt a piece of memory which determined the the actual technical details. It doesn't matter that much for now, but essentially it was a problem where a piece of memory was being used by two different components, and it hadn't been correctly zeroed out after one part of the program had used it. It then got used in another place without it being zeroed out. Ends up being a problem that when you end up catching a Pokemon or discovering this Pokemon, it comes up with this very weird thing called, it says missing, its name is missing no, like missing number, and it's got a very strange, distorted, like glitchy looking image on the screen. And this was a very weird state. You saw it, it was like, what is this? This was leveraged by people to create an exploit which would give you infinite rare candies, which would level your Pokemon up to the maximum level. But you could put your game save file in really messed up states if you ended up doing things like, if you didn't just ignore the Pokemon and move on after you'd used it in your exploit. If you actually captured it or tried to do things with it, it would just completely trash your game save. So the idea of the weird machine. That's the idea of the weird machine. So when we are looking at exploitation, we can think of it in terms of actually programming this weird machine. So it's, as I was mentioning earlier, it's often hard to distinguish from the processor's level the difference between code and data. So data is code, code is data is an interesting way of thinking about it. It's all a matter of perspective, really. So if you think about, as an example, if you think about an SQL injection attack where you're actually writing SQL code and passing it into a function, is that code or is that data? You're passing it into a function as data, but then you're manipulating the program, you're manipulating the program in a way that it will then inject your data into the code to get run as code by the machine. The same goes for things like shellcode that you're writing when you're passing it in into like standard in to exploit a buffer overflow as like the payload to a buffer overflow vulnerability, buffer overflow exploit. So it's all very very interesting, and I'll upload the slides with the references. So thank you very much for listening. Thought I better just quickly add this to the end. So I discussed the missing no bug in this slide, but I didn't actually have image, so I just thought I'd include it. So yeah, this is obviously a very strange state for the system to be in. Yeah, I thought I better quickly throw that on the end, and here are the reference slide. The links are all available in the description box down below. Anyway, thank you very much for watching.